From your previous study of oscillators, you've learned that frequency stability is of the utmost importance. You might ask, why all of the concern about frequency stability? As an example, let's consider a radio broadcast station. I have here a book of FCC regulations governing the operation of radio broadcast stations. One particular regulation prohibits the frequency of the station from changing more than a few cycles, and it's a pretty stiff regulation. But it must be so that the station will not interfere with another station operating on a nearby frequency. Now, for this reason, the oscillator producing this frequency must be one with the very best frequency stability. An oscillator capable of producing such an output is the crystal-controlled oscillator. We're not going to study the oscillator circuit in this lesson, but we will study the characteristics of the crystals used in such a circuit. And here I might add that the crystal will be used as the frequency determining device of the oscillator, in much the same manner as the coil and capacitor was used in oscillator circuits previously covered. Now, some of the items that we're going to discuss are the use of crystals, types of crystal substances used, crystal cutting, types of crystal cuts, crystal characteristics. We'll see the purpose of a crystal holder, the frequency stability of crystals, and a little bit later we'll discuss overtone crystals. Now, there are many types of crystal substances, but not all are suitable for use in oscillator circuits. A crystal used in oscillator circuits must possess a characteristic known as piezoelectricity, or the piezoelectric effect. Let's look at a definition of the piezoelectric effect. Now, the piezoelectric effect is defined as the property of a crystal by which mechanical stress produces electric charges, and conversely, electric charges produce mechanical stresses. Now, at this time, you should complete item 1 of your TVI guide. Now, this is saying nothing more than if a voltage is applied to the crystal, it will vibrate. The amplitude of these vibrations are much greater at one frequency than at any other frequency. Now, this one particular frequency is called the natural resonant frequency of the crystal. Now, let's look at some of the crystal substances that possess the piezoelectric characteristics. They are Rochelle salt, tourmaline, and quartz. Now, we should include these substances in item 2 of the TVI guide, the A part of item 2. Now, of these three, Rochelle salts exhibits the piezoelectric effect to the greatest degree. However, quartz crystal is most generally used because it has a greater mechanical strength. Now, at this time, let's complete the B part of item 2. The substance most often used in oscillators is, go ahead and complete that blank. It is quartz crystal. Remember, it has a greater mechanical strength. Now, I want to show you a piece of quartz crystal in its natural form. Now, if we were to examine this carefully, we can see that the quartz crystal has a hexagonal cross-section. That is to say, it has 6 sides. Now, also, quartz crystal in its natural form has pointed ends. This one doesn't because a primary cut has already been made on this crystal. Now, let's take a look at this drawing so that we can determine more about the quartz crystal. There are 2 views. The top view indeed shows us that the quartz crystal has a hexagon shape, 6 sides. While the lower view points out that indeed the quartz crystal in its natural form does have pointed ends. Now, quartz crystal in its natural form cannot possibly be used in oscillator circuits. It must be cut in a specific manner to exhibit its piezoelectric properties. I know all of you at one time or another have heard of diamond cutting. The reason a diamond is cut is to give it brilliance, and the manner in which it's cut will determine its degree of brilliance. Now, a piece of diamond in its natural form would never be used in a diamond ring, just as a piece of quartz crystal would never be used in an oscillator circuit. Now, when a piece of crystal is going to be cut, imaginary lines are used as the reference points for cutting. And these imaginary lines are known as crystal axes. Let's take a look at this drawing of a crystal and see the exact location of the crystal axis. The axis passing from point to point, or end to end, and directly through the crystal is known as the z-axis. Remember, from end to end, directly through the center. The axis passing through the corners of the crystals is known as the x-axis. Remember, it goes through the corners. While the axis perpendicular to the faces of the crystal is known as the y-axis, going through the faces. Now let's remember these are only imaginary lines and are used as reference points when cutting the crystal. Then at this time, complete item 3 in your TVI guide by labeling the axis there. Now, all crystals are not cut in exactly the same manner, just as all diamonds are not cut exactly the same. The properties which a crystal exhibits are dependent on the manner in which it's cut. Now, there are many different cuts, but we're only going to examine 3 basic cuts. Let's go to this chart and see exactly how we make these 3 particular cuts. The first cut is made perpendicular to the x-axis, which you will recall passed through the corners of the crystal, perpendicular to that axis and parallel to the z-axis. Now, to get a more realistic view of this cut, let's go to a mock-up. Remember, we're considering the x-axis passing through the corners of the crystal. The cut is made perpendicular to this x-axis and parallel to the z-axis. And the cut would look something like this. You can see that it's only a small portion of the natural crystal. Now, since this cut was made in reference to the x-axis, it is known as an X-cut crystal. Okay, let's go back to the chart and see how another cut is made. For this cut, we will use the y-axis, which passed through the face of the crystal. This cut will be taken perpendicular to the y-axis, and it also is parallel to the z, which you will recall ran through the center of the crystal. Remember, perpendicular to the y, parallel to the z. And again, to get a more realistic view of this cut, let's go back to the mock-up. Remember, the y-axis passed through the face of the crystals in this manner. We'll cut perpendicular to that and parallel to the z-axis. And we come up with our second cut, which in this case, since we took it in reference to the y-axis, would be known as a y-cut crystal. Then let's go back to our chart for the third and final cut. Now, this time we're going to cut at an angle from the z-axis. Recall, the z-axis passes through the center of the crystal from end to end. And for this cut, we'll cut at a 35-degree angle from the z-axis. Remember, 35 degrees from this z-axis. Okay, back to the mock-up once more. Now, in this case, the crystal cut is taken right in, or made right into the face of the crystal. Remember, the z-axis is running down through the crystal in this manner. And we'll cut at a 35-degree angle from this z-axis. And removing the cut from the crystal, again, only a small portion of the natural crystal, we call this cut an AT cut. An AT cut crystal. Okay, let's go back to our chart once more, and I want you to complete item 4 in the TVI guide. Now, we've seen from the mock-up what these 3 cuts look like. Let's go over, and I want to show you the actual cuts now. I have here 3 crystal cuts. Now, as you can see, they look like small, thin wafers, and each cut looks very similar. Each cut looks very similar. Now, all crystals look the same, but not all will exhibit the same characteristics. Now, you'll recall earlier, we mentioned the resonant frequency of the crystal. Not all crystals, naturally, will have the same resonant frequency. Its frequency